Excited to hear about this bizarrely impossible idea of time parallelization.
Thank you, Hillary. And I should thank the organizer and the Newton Institute who have invited a strange, I guess the title of the session was given probably because of my talk. So it's about okay. Okay. It should work. Yes. So parallel algorithm for weather prediction and climate. So it was put into the novel ideas or novel methods, but actually it is not. It is a very old method, and so talk a bit about the origin and why we should eventually worry about it in NWP. And I have to say that I'm cheating a little bit because all I'm doing is PDE on the sphere or PDE on the line. So I have PDE on the circle, so I'm not at PDE on the sphere yet. So I will try to explain the schematic of time parallelism for initial value problem. I will describe one algorithm that I'm using. It's so simple that everybody will understand. And then if time permits, I will go through some of the applications that I've done as a first step. And I guess there's more work in the future than what has been done up to now. So time parallelism goes back at least to 1964. It's from last century. So this fellow was a warrior. So he started to worry in 1964. He asked himself, what will happen if we get too many cores, too many CPUs for our applications? So we won't be able to use all of them to solve our PDEs equation on the sphere, like evolution equation. And he said, well, maybe we have to split and parallelize also in the time direction. And the purpose of that was also to obtain real-time solution. Because for weather forecasting, for instance, the goal is to reduce the real-time forecasting so that eventually you increase resolution, but you still meet the delivery requirement. So his main idea was, and that has been used for all those old folks that have used a vector computer. That's an old trick, is well, sometimes it's easier to parallelize if for certain things you redo the computation rather than communicate it. So that's one way of reducing real time. So you can, if your goal is really to use the real time and you have many processors that you have paid for, then the goal of the game is to use all of these processors to reduce your real time. So one of the beneficiaries obviously is numerical weather prediction, and that was his worry there. When computers are capable of executing many computations in parallel become available. So that's yesterday. So why time parallelism? So it's obvious that there is a limit to parallelization in space. And for all of the models that I know, parallelism is only done on the horizontal, not on the vertical. So if you work at if you set your goal at a fixed resolution, then you have a number of grid points, and there is an optimal number of grid points that you can put in a processor. Otherwise, you're wasting it. So you're just paying the electricity for nothing. And so if there is a limit in the resolution and a limit in the number of points per processor, then the number of processor per job is limited. Therefore, if you have 10 times as many or 100 times as many processors as the number required for a job, then the only room for increasing the real-time efficiency is to parallelize along the time direction. And so that's my hypothesis, but still a long way from being reality, but it's coming. So here's the idea. Suppose that we have the solution, the sequential solution of an ODE or PDE at every small delta time step delta t over a certain period. If we were to sample the solution at every large delta t, so a certain number of times, and big N, and then we could start from these, let's say, checkpoint and integrate as initial condition for a shorter period, but all these could be done in parallel. So the real time of the second integration would be much smaller than the real time of the first one. And they should produce the same result because initial value problem have unique solution, and if they don't, it means that you can't choose which one is good. So to take advantage of that, then, if you have reduced the real time, well, it will not hurt too much maybe if you did 2 or 3 iterations. So that's more or less the idea of parallel time integration, is to start from a first guess for these checkpoint value, do many integration in parallel, correct your first guess, and repeat until convergence. And hopefully it will converge in 2 or 3 iterations. So that's in theory. Now, the way it has been implemented in the parallel algorithm is a direct method in disguise. The way you do this correction step is such that if you iterate the number of times that with the number of iteration is equal to the number of slices, then you converge to the exact solution. So it's a direct method in disguise, but because it implies a lot of work, we don't want it to converge at the end. We want it to have a very fast convergence rate. And another important concept is that you don't need to converge to machine accuracy. You only need to converge to the accuracy of your fine integration. So here's for those that the more modern people with that prefer to look at pictures. So we start with in this graph I put the cross solution is a bunch of straight lines, and the fine solution is a bunch of curves. And then you see that there is a discrepancy at the end of this fine integration and the start of this coarse integration. So, and the way to go about the iterative method is to try to find a correction algorithm that will decrease these values. So this is a root finding problem, more or less. You want to find these values and such that you want to reduce the blue arrows to 0. And it's very simple in practice. So you have your model, you integrate for a certain period of time, a certain number of time steps, and this is on the course time step, of course, and then you get a first guess, and then you iterate, and then there's one part of the iteration that can be done in parallel. So this is one time step of the coarse integration and m time step of the fine integration. So this is what you compare at the end, and then you correct for, so you take the n value, for those that know MATLAB, this is just the last value of the field, and then you start another sequential loop, but then you have to put a source term in there, because you know that if you start from the same condition, it will always give the same condition. So you add a source term so that eventually it will converge to the fine solution. So this is your, this is your coarse grid integrator again. You do one time step, but you make a correction here. This is equivalent to adding a tendency to that equation. And you can see that at convergence, the 2g's will go to 0, and the u's will go to the f. And that's what you want. You want the f is for the fine solution, and g is for the grossier, coarse solution. Okay. So, as I mentioned, at convergence, your starting condition for each fine integration is what you would have had if you had done a serial integration. So there's no gain. You will not improve on the solution. You will just recover it. The gain of efficiency, of course, is related to the work you do and the number of time you iterate. So to maximize efficiency, you have to converge in the least number of acceleration. You need to converge in the minimum number of iteration, which is 2. And efficiency, well, it can be. Since I'm interested in real time, that's really what matters for me. So there were some analysis in the time done by many people, Staff and Ronquist in BAL. Actually, the algorithm, one of the algorithms was developed by Jacques Willion, and they are the people that work with him. And he died shortly afterwards. But his work is taken up by Madej, and he has a big school trying to find out direction of application, and some other people are taking it too. So an analysis of stability was done a few years ago. So we just consider this schematic equation. And what was found was that it could be unstable if mu was purely imaginary. It's very unfortunate because for a meteorological problem, this is what interests us most. So it can be unstable. I'll give you an example later on. But there exists a workaround, or some workaround. There is you could put a linear algebra problem on top of the solver, and you, at least for linear problem, that can solve. And then there's a variant of the Peter, which is called Peter, which is another similar algorithm that that can solve this problem in the nonlinear case. There was some convergence analysis by Madej, Gander, and so on. If it converges very well. But the problem is if it converges. So here's so all the results that I show here are the results published in the literature, but since I'm never sure that I understand perfectly, so I code the thing and I see if I reproduce the picture of the paper. So I more or less did. So, and I think the difference is because I'm using a more recent version of MATLAB that is with much finer resolution. So in red here, so I'm considering implicit Runge-Kutta, Rado-tree. And Runge-Kutta, what they do is that they build the Padé approximants of the exponential factor. And so it's implicit, so it's usually stable. But of course, we do the combination of both. So with the small time step and with the large time step. So in this case, I'm just using the same integration method for the fine and the coarse integration, but they could be very different, and they could be done for a partial differential equation. They could be done at a different resolution as well. So in this simple case, one can obtain the amplification factor for each iteration, and one looks for the maximum of that to be 1. If not, it's unstable, at least for a while. So I'm plotting the instability domain. But in that case, being unstable means that it will not converge in finite number, in a fast iteration. But I know that if I do enough iteration, it will give the correct result. But and that'd be interesting. These are done for different ratio of the large and small time step. So what is distressing is these red area, red for danger. So these are places where off the imaginary axis that they don't converge. But so given that, we could all leave and say, okay, it's not worthwhile. So I'll pass quickly on the number of applications. The paper in blue is because I collaborated with Gander and tried to reproduce all the results that he had done. He has done a lot of work on that algorithm, and he produced this solution for the instability. So I made an original contribution yet. I look at the similar Granger algorithm. You can obtain the amplification factor analytically. And for numerical weather prediction, Gander has looked at the Lorentz equation. He's an applied mathematician, so for him that's meteorology. But the German Weather Service, DWD, has started some work with the modified parallel, but I think they may not have. They published something that said, well, it's feasible, so it encourages me. So my project is to have a stable and accurate method working and study the different choices of the algorithm, which is, of course, if you have two different algorithms, then you multiply the number of possibilities. Here's my roadmap. At the moment, I have on a 1D problem. So the first steps I've told you, I produced the results already published. I'll go quickly because it did work in the case of Berger's equation with some diffusion. But here and I looked at the pure oscillator, which is supposed to be unstable in that case. And here is the original method here. You can see the coarse solution is in with the circle, and the fine solution is with the stars. And you can see that, well, you have some convergence, but not quite. But there's a caveat here. This is supposed to be a pure oscillatory problem, and the fine solution is decaying. So this is an integration scheme that I would never have used. So it didn't converge anyway, but it should have converged to this fine grid solution. But with the modified method, which gives us hope, you see the initial guess, fine solution, and the first iteration. So you transform an ODE problem into a linear algebra problem. So I'm not. So this is very expensive, but at least it worked in that context. So research is to have it work for a more general context. So this gives hope, and this is for the future. From 0 to 100 miles per hour in 10 seconds.
Is your coarse model coarse in space as well as in time?
Yes, that's an answer. Yeah, you can have reduced grid in space eventually. And I have an example where that works, but I'm not quite satisfied with it.
So in that case, I can't quite see how information about the small spatial scales can propagate from the initial time to the final time. Because
I have to investigate that. I just concentrated on recovering the results of that paper. But you can see that this is constant advection with limited area. So you feed at one place with the method of characteristic. So you feed the solution initially, of course, but then you keep feeding it on one side, and you know the advection speed. And the trick that was used here was that you could forecast when the fine solution was the correct solution, which usually you cannot. So in that case, if you do 3 iteration, for instance, you see that the error is being flattened from one side and from the next. So eventually it will reduce to 0. But you see the convergence because there is no reduction in that error here. You see that the convergence rate, because this is max norm, is stay flat and then drops suddenly to 0. So it's not a completely satisfactory result. But to come back to your thing, this time scheme is like a multi-grid, multi-dimensional multi-grid in both space and time. So it should work. But in the application that I've done, there was a very aggressive coarsening, like of the time scheme. So maybe that has to be worked out, like the ratio of coarse step to large step.
It looks like some of the things, I know it's not doing the same thing, but it's a bit like the way Yannick Tremollet paralyzes
Yes, well, I wanted to say that your European Center, the way they do the data simulation, because they have a variational 4D time integration and the S simulation, they can start the integration even before they have all the data in, and because they iterate, eventually
they run all the windows in parallel. Think of your
I did not look at all the detail, but it seemed that there was some similarities there.
More questions? Thanks, Jean, once again.